Welcome back to the crash course in piping stress. If you're new here, piping stress analysis is basically the engineering discipline that makes sure the pipes carrying steam, oil, gas, or chemicals through a plant don't crack, leak, or collapse over their lifetime. In Module 1, we probably introduced the big picture. In this module, Module 2, we're going to answer two very practical questions. What actually pushes, pulls, and twists a pipe while it's in service? And what does that do to the metal itself on a microscopic level inside the pipe wall? By the end of this video, you'll be able to look at any pipe in a plant and start thinking like a piping engineer about what forces it's dealing with.
Here's the roadmap for this module, broken into 3 simple stops. Stop 1, load classification. We'll learn that every force acting on a pipe fits into just one of 3 buckets: primary, secondary, or occasional. Don't worry about those words yet. We'll build them up slowly. Stop 2, primary versus secondary loads. This is really the heart of the module because these 2 types of loads behave in almost opposite ways, and understanding that difference is one of the most important ideas in all of piping stress analysis. Stop 3, resulting stresses. Once we know what's pushing on the pipe, we'll translate that into the actual stress happening inside the pipe wall, the longitudinal, radial, hoop, and shear stresses. These are the numbers engineers actually calculate and compare against code limits.
Let's start with the big 3 categories. First, primary loads. These are the loads that are there all the time, every single day the pipe is in service. Think of the pipe's own weight, the weight of whatever fluid is flowing inside it, water, oil, steam, and the internal pressure pushing outward from the inside. If the pipe is buried underground, you'd also add the weight of the soil sitting on top of it. The key idea: primary loads never go away. Second, secondary loads. These show up because of how the system operates, not just because it exists. The biggest example is thermal expansion. When hot fluid runs through a pipe, the metal heats up and physically grows longer, the same way a metal ruler expands slightly in the sun. That expansion pushes and pulls on the piping. Other secondary loads include a support settling slightly into the ground over time, or vibration from a nearby pump or compressor. Third, occasional loads. As the name suggests, these don't happen often, maybe never for the life of the plant. Wind blowing sideways against an elevated pipe rack is one example. An earthquake shaking the ground is another. You design for these as a safety precaution, even though you hope they rarely or never actually occur. Let's zoom in on primary loads because they have a very distinct personality. The sources are straightforward: the piping's own metal weight, the weight of the fluid it's carrying, the internal pressure of that fluid, and, for buried pipe, the soil on top. As an example, internal pressure alone creates something called hoop stress. There's a simple formula for it. Hoop stress equals pressure times outside diameter divided by 2 times wall thickness. Don't worry about memorizing that right now. Just notice that it's a direct, simple relationship between pressure and stress. No complicated behavior, no timing involved. Now, here's what makes primary loads special, and this is worth really understanding. First, they're force-driven. That means they come from an actual force, a weight pressing down, a pressure pushing out. It's not caused by something bending or moving. It's a direct push or pull. Second, and this is important, they are not self-limiting. Imagine a heavy object sitting on a shelf. If the shelf starts to crack, does the weight on it get any lighter? No, it keeps pushing down just as hard, right up until the shelf breaks completely. That's exactly how primary loads behave. If the pipe starts to fail, the weight and pressure don't ease off. They keep acting at full strength, which is what makes primary load failures dangerous. Third, they're not cyclic, meaning they don't turn on and off. The weight of the pipe is there Monday, Tuesday, every day, all the time, at roughly the same level. And because of all this, a primary load failure can happen from just one single event. Think of a pipe bursting under pressure or a support collapsing under weight. There's no need for repeated cycling. One bad moment can be enough. Now, let's contrast that with secondary loads, because they behave almost the opposite way in every category. First, secondary loads are displacement-driven, not force-driven. That's a key distinction. Instead of a direct push or pull, something is moving or deforming, and that movement creates stress. The classic example is thermal expansion. As the pipe heats up, it wants to grow longer. If it's constrained by supports or connected equipment, that growth generates internal stress, not because someone is actively pushing on it, but because the pipe's own shape is changing. Second, and here's the really important part, secondary loads are self-limiting. Go back to that metal ruler expanding in the sun. As it expands and pushes against whatever's restraining it, the pipe itself flexes and bends slightly, which relieves some of that built-up stress on its own. The system essentially self-corrects. This is fundamentally different from primary loads, which just keep pushing no matter what. Third, secondary loads are typically cyclic. They turn on and off. Thermal expansion is a perfect example. It's present when the pipe is hot and running, and it essentially disappears when the pipe cools back down, say during a shutdown. So the pipe is basically flexing back and forth, heating up and cooling down day after day, startup after startup. And that cyclic back and forth nature leads to the failure mode for secondary loads, fatigue. Think about bending a metal paperclip back and forth. The first bend doesn't break it, but bend it enough times and eventually it snaps, even though no single bend was especially forceful. That's fatigue. It's why a piping system might run perfectly well for years, even a poorly designed one, before a crack finally develops from the accumulated cycling.
Let's finish the load categories with occasional loads, the ones that only show up now and then, not as part of normal everyday operation. Wind load is exactly what it sounds like. Wind pushing sideways against a pipe, especially pipes that run above ground on open racks, exposed to the weather. It creates a lateral, sideways force on the piping and its supporting structure. Earthquake, or seismic load, is the dynamic shaking transmitted into the piping when the ground itself moves during an earthquake. Since these events are rare, and hopefully never happen at all during a plant's life, they're treated differently in design codes than the loads that are present every single day.
Now let's lock in the difference between primary and secondary loads with a clean side-by-side comparison. Because if you remember only one thing from this whole module, this is it. Driving mechanism. Primary loads come from force, weight, pressure. Secondary loads come from displacement, thermal growth, a support settling. Is it self-limiting? Primary loads? No. They keep acting at full strength even as the system starts to fail. Secondary loads, yes. As the pipe deforms, the stress relieves itself. Cyclic behavior. Primary loads stay essentially constant, day in and day out. Secondary loads are typically cyclic, present under one condition, like hot operation, and gone under another, like a cold shutdown. Mode of failure. A primary load can cause failure from a single application, like a burst. A secondary load causes failure through fatigue, the slow accumulation of many stress cycles over time. Why does this matter in practice? Because engineers actually evaluate and set allowable stress limits differently for primary versus secondary loads, precisely because they fail in such different ways. So now we understand what's pushing on the pipe. Let's talk about what that actually does inside the metal, because stress, in engineering terms, isn't just a feeling. It's a very specific, measurable quantity, force spread over an area. There are four main types of stress that show up in a pipe wall. Longitudinal stress runs along the length of the pipe, the same direction the pipe travels, like stretching a garden hose from end to end. Radial stress happens across the thickness of the pipe wall, caused by internal pressure pushing outward. Imagine squeezing the wall of the pipe from the inside toward the outside. Hoop stress, also called circumferential stress, wraps around the pipe's circumference. Picture the metal hoops that used to hold together a wooden barrel. Internal pressure tries to push the pipe wall outward, and in effect tries to split the pipe into two halves lengthwise. This is usually the single biggest factor engineers consider when deciding how thick a pipe wall needs to be. Shear stress comes from twisting, or from forces that slide layers of material past each other. Think of wringing out a wet towel. In piping, this comes from torsional loads, or transverse forces acting on the system. Let's connect the dots between the loads we talked about earlier and these four stress types, because in practice, one stress type can come from more than one kind of load. Longitudinal stress, for example, can come from a straightforward axial force, like weight pulling down the length of the pipe, or from internal pressure itself, or from bending, which happens when weight, pressure, thermal expansion, or wind causes the pipe to flex like a diving board. Hoop stress and radial stress both come primarily from pressure, whether that's pressure from inside the pipe or, less commonly, from outside. Shear stress can come from a transverse force, something pushing sideways against the flow direction, or from torsion, a twisting action. And again, this can trace back to weight, pressure, thermal expansion, or wind. Notice something interesting in this table. Many of these stresses are labeled primary or secondary because the same type of stress, say bending stress, could be caused by a primary load like weight or a secondary load like thermal expansion. What matters isn't just which stress you're calculating, but understanding which category of load created it, because that tells you how to judge whether it's dangerous.
Let's bring it all together with a recap in plain language. 1. Every load on a pipe is either primary, always there, like weight and pressure; secondary, tied to operating conditions, like thermal expansion; or occasional, rare events, like wind and earthquakes. 2. Primary loads push from force and never let up, even as failure starts. Secondary loads push from displacement, and they ease off on their own as the pipe flexes. 3. Because secondary loads cycle on and off, their danger isn't a single bad moment. It's the slow buildup of fatigue over many, many cycles, sometimes over years. 4. All of these loads, working together, create longitudinal, radial, hoop, and shear stress inside the pipe wall. And hoop stress is usually the one that decides how thick your pipe wall needs to be in the first place. That's the foundation. In the next module, we'll take these ideas and see how engineers actually combine different loads together, following ASME code rules, and how all of this gets set up practically inside CAESAR 2, the industry standard piping stress software. See you there.